All right, ladies and gentlemen. This class recording has started. So, that's going to be loud, but oh well. Okay. Up on the board. Up on the board. Folks, you close the door for me. I'm sorry. I forgot that the class is out. All right. Settle in. All right. Up on the board. The 4 questions dealing with mechanics. Have we covered these enough now? Are we good with these? Okay. So, right, where is the object? We call that position. What's it doing now? We can talk. Okay, go ahead. Velocity or speed, depending on how much information we need. What will the object be doing in the future? Acceleration, right? Yesterday, we talked about acceleration in more detail, defined as the rate at which velocity changes, right? How much does the velocity change over the time that it takes for that change? That's going to be important a little bit later on, so make sure we remember this definition. But yesterday, towards the end of class, we talked about the idea that velocity can change in 3 ways. What are the 3 things that can happen that would be considered a change in velocity, which would, by definition, be considered acceleration? So what's the first thing that can happen to something that we would consider to be acceleration? We can talk, come on. All right, so first thing, right, speeding up. If velocity increases, that's a change in velocity. That's considered acceleration. Did we talk about the numbers a little bit with this or no? Right? Here, let me go this. Acceleration is defined this way. First, the delta V, right? What does the delta mean? Change, right? So we're talking about the change in velocity over time. We also talked about the idea that, my computer decides to, there we go. We can write the equation that way, right? Because in order to calculate the change in something, you have to know where it starts and where it finishes. If something speeds up, which one's bigger, VF or VI? VF. So if we do a mathematical calculation here, right, if VF is greater than VI and we're subtracting, on the top of this equation or fraction, we'd end up with a positive number. So when something speeds up, we could also refer to that as what? It's acceleration, but what kind of acceleration? Positive acceleration, right? However, there are 2 other things that we could consider acceleration. What else could we consider acceleration? Right? When something slows down, its velocity is changing, and therefore that would be acceleration as well. If we go back to this, right, when something slows down, which one is bigger? VF or VI? VI. So when you do this mathematical calculation, you're going to end up with what? A negative number, which means slowing down we could also consider to be negative acceleration. And the third thing that we talked about was changing direction, right? Velocity is a vector quantity, meaning that it tells us magnitude and direction. Even though we may not go any faster or slower, oh yeah, even though we may not go any faster or slower, if we change the direction that we're going, that is a change in velocity, and that counts as acceleration as well. Okay? Good there? All right. If you would please, we can put that outline away and go to these slides on graphing motion that we started before exams, but we didn't finish. Let's talk about the rest of this here and put some of these things together. Okay? All right, in general, excuse me, we make graphs in order to recognize patterns, see relationships better, etc., etc. The first type of graph that we talked about was the position versus time graph. We said a position versus time graph tells us two things. What does it tell us? Position and time. So it tells us where something is at a specific time. But we also use the position versus time graph to tell us one other thing. In a sort of obvious kind of way, position versus time graphs tell us where something is and when it's there, but it also can tell us what. What else did we use the position versus time graph to find? Heard it. Velocity, right? How do we tell the velocity from a position versus time graph? From its what? From its slope, right? That slope being rise over run, distance over time, that's velocity, right? And we talked about a bunch of different graphs, right? That if we have a position versus time graph that's horizontal, this object is at rest, right? Because the position isn't changing as the time is. Straight lines represent an object moving with a constant velocity because straight lines have a constant slope. And we talked about this kind of graph where we have two parts, two straight lines on this graph, one steeper than the other, and that means one's going faster than, or one part is going faster than the other part. And then we added this graph, right? What's happening? What did we say we introduced here in this graph? What's happening here? It's velocity, but what do we see about that velocity? It's negative, right? A negative velocity means we're doing what? Not slowing down, but going backwards. This is still a constant velocity. It's just a constant velocity in the other direction. And then we added in curved lines. Curved lines do not have a constant slope, meaning that if we have a curved line on a position versus time graph, what's happening? We can sum it up in one word. If the line is curved on a position versus time graph, it's accelerating. Its velocity is changing. Sean, specifically, what's happening in this graph right here?
It's accelerating and
So let's go with it's slowing down, right? Because the slope starts off very steep, right? But then gets more and more and more shallow, okay? We just talked about that slowing down we could also refer to as what? Got some help? What else could we talk about as, what else could we refer to slowing down as? Negative acceleration, right? Here, what's happening in this graph? It's speeding up, right? This is the graph you made of your marble. What kind of acceleration? Positive acceleration, okay? Good there. All right, let's throw you for a loop, hopefully, or hopefully not. So, all right. Next graph, like it says up at the top, describe the motion of the object, okay? First, it is a straight line. However, we've made one change to this graph, right? What's the big change that we have to consider here on this graph? Okay, go ahead. It's a velocity graph, or technically it says speed, but, you know, kind of the same idea. What's happening in this graph? Actually, you know what? Describe the motion of the object. Talk to the person next to you. Go. several ways we can describe this motion. If we were watching the object that was being graphed here, what would we see is happening to it? It's getting faster. Even though the line is straight, because this line is representing speed, this object is getting faster and faster and faster and faster and faster. What else could we say about this object? We could also say that it is okay. Yes. Right. There's something else I'm going for here. True. All right. Think about what we talked about. What first thing we talked about today, right? It is accelerating positively, right? It's getting faster and faster and faster. So, first, right? This is a velocity versus time graph, and in an obvious kind of way, right? What is a velocity versus time graph going to tell us? Velocity and time, right? Time on the x-axis, velocity on the y-axis. Okay? But in an indirect way, it can also tell us the acceleration if the velocity is changing. In this graph, even though it is a straight line, this is not a constant velocity. It is a changing velocity. This object is accelerating. Okay? Good there? Next picture you guys have looks like this. Talk to the person next to you. Describe the motion of this object. Go. All right, let's discuss. So, first part of this graph, right here, right? What's happening during that section right there from 0 to 10? It is moving, but it is moving with a constant velocity, right? Okay? Make sure we know what kind of graph we're talking about. What happens from 10 to 20? 10 to 20, that object is slowing down. However, which way is it moving? Okay. All right. One thing we have to keep track of on here, right? We talked about that velocity is a vector quantity. It has to tell us how fast, but also which way. We do that with positive and negative, right? This section of the graph, if we broke it down into a bunch of ordered pairs, right? Graphs are just a collection of ordered pairs. All of the y values, that's not what I wanted to do. All of the y values during this section right here would all be positive. They would be getting smaller, but they would still be positive. If something has a positive velocity, that means it's moving which way? Forward. So even though this line slopes downward, it's still moving forward, it's just getting slower. Okay? Good there? All right. The last two slides down on the very bottom talk about this graph. And then there are 6 questions that relate to this graph. I would like you to take a couple minutes, talk to the person next to you, and answer these 6 questions. All right? I'm going to put the graph up big up on the board here. So if you need it, you can look at it there, although you have it next to you. But here's a bigger version of it. So I'm going to pause the recording for a couple minutes while you guys talk. then we'll come back and we'll discuss together as a group. So the 6 questions relating to this graph on the bottom part of the slides that I gave you last week. Go. All right. All right, let's discuss. So, first question states, when is the object at rest? On this graph, what represents rest? What does the velocity have to be in order for the object to be at rest? 0, right? There are 2 parts where this graph is at rest. Right here and right there. Okay? Because in both of those sections, right, the graph is along the x-axis. And ordered pairs that are on the x-axis have a y value equal to what? 0. Okay? Good there. Okay. Next question. We'll go right next. When is the object traveling forward with a constant velocity? Right there. Okay? It's traveling forward. We know that because... Why do we know it's traveling forward? Why do we know it's traveling forward? It's positive, right? It's a constant velocity because you plateau, right? The y values during that section are the same. Good there. Okay? Next question. Go blue for this one. When does the object turn around? In order for it to turn around, what has to happen to our velocity? It has to go from being positive to being negative. So we could say, like somewhere along there, right? There's not a specific spot where it turns around, okay? That's the only place where the graph goes from being positive to being negative, right? On this graph, that's what has to happen in order for it to turn around. Okay? Good there? All right. Next question. When is the object traveling backwards with a constant velocity? When is the object traveling backwards with a constant velocity? Answer? It isn't. Ever. Right? There is no time during this section of the graph where the velocity is constant. Right? It's always changing as it's moving backwards. Constant velocity is a flat plateau. There are no flat plateaus there. Okay? Good there? All right. Let's go. I'll go purple for this one. Motion of the object from 25 seconds to 60 seconds. So on your graph, that would be from here to here. What's happening to the object during that time? Physically. Good. It's speeding up. What else might we throw into that? It's speeding up while... Speeding up is accelerating, right? It's speeding up while going forward, right? Because those values are all where? Above the x-axis, right? They're all positive, okay? All right, and then, finally, as far as a tricky one goes, this is pretty tricky. All right? The motion of the object from 500 seconds to 600 seconds. Oh, wrong way. From here to here. Physically, what's happening there? It's slowing down. Even though the line tilts upward, right? It's getting closer and closer and closer to what? It's getting closer to 0. And that means something's slowing down. It's slowing down while moving which way? Backwards, but it's still slowing down. Okay? Okay, good. Yep. From 300 to 500, right? Even though this isn't one of the questions, right? Over here, orange, right? From here to here, right? Even though the line tilts downward, right? Physically, it's doing what? It's speeding up. It's just speeding up while it's going backwards, right? Technically, right here at this spot, right there, what can you tell me about that part of the graph? Why is that part of the graph significant? Talk to the person next to you. Why is that part of the graph significant? All right, so here we go. All right, that circle, that part that I circled in red, why is that significant on this graph? What'd you come up with? Any ideas? Good. Okay. That happens right here as well. It starts getting slower at that point too. Why is that point down at the bottom that I circled? What's significant about that point? Okay, go ahead. Okay, I'll give you that. Okay? It has the highest velocity, which means what? It has that is the fastest that car is traveling at any point on the graph. Even though it's the lowest physically on the graph, right? It's still the fastest, it's just going which way? Backwards, right? That spot that I circled originally, this one down here, is the fastest that object, whatever it is going on this entire graph. Okay? Good there. All right. Because it is 12:05 already, don't want to get into the next stuff that we're doing, so we will save that packet I gave you today for tomorrow, and we'll start doing some more number stuff tomorrow. Okay?